Hello, this is Bernie Ziegler, and this is part two of recent advances in theory of modeling and simulation, implications for computational emergence. Let's take a more formal look, although not fully formal, but graphically, into how closure and decoupling actually can be proved. Let's consider devs subclasses. So we have a basic subclass of devs, and using devs specification, it specifies a subclass of dynamic systems, Y-more systems. We also have coupling, and this leads to a set of possible coupled models based on the subclass. By dev specification of coupled models, this leads to a definition of coupled subclass of systems in the class of all dynamic systems. Now the question is, if closure and decoupling holds, then this coupled subclass of systems actually is contained, included within the basic systems that we started with, that were specified by the basic subclass. We just talked about subclasses, but actually there's a difference between subclasses and variants of devs, and this diagram is the first of two, which we can start to understand how that looks within the modeling and simulation framework. So our framework that has been expounded in the other publications talks about a source system, model, and simulator, and distinguishes those three entities as well as relations between them. And a new entity that is not usually distinguished in simulation packages, the experimental frame, which characterizes the conditions under which a model or a source system will be experimented with. And that represents the objectives that we have in constructing the model. So what kinds of input-output we're looking for, and how will that contribute to the purpose of building the model. Now we can distinguish types of systems being different kinds of source system, and types of problems as increasing the set of models that can be constructed. So we distinguish between types of systems, which will be variants of devs, and types of problems, which will be subclasses of devs. So here you see that we have the dynamic system expressed now all in UML, in the UML modeling kind of relationships, and we have the modeling relation as a potential relation between the dynamic system and the simulation model. And this model is formalized by the devs discrete event specification, which can be a devs coupled model, which is closed under coupling. That remains to be proved. Or a devs extension, which can be a devs variant or a devs subclass. So a variant of devs is an extension that has closure and decoupling and allows adaptation of the original formalism to describe new types of simulation models, while a subclass of devs is an extension that is closed under coupling that is more specific than devs, and in some contexts can be reduced to at least to an equivalent devs model. We'll look at some examples of closure and decoupling and a non-example as well. We'll talk about some subclasses called ML devs, routing devs, multi-p-devs, devs Markov, and a non-example which is the min-max devs. And the extending the concept to iterative system specification in general, for example, sample-based iterative specification. Multi-level devs, ML devs, is developed to characterize problems in biology where you have to keep track of the components of a cell as well as the cell itself and their interrelationships. So you have two levels of organization, and you want to have very dynamic capability for coupling. So we have intentional or implicit coupling, and proof by Steniger and Ermacher recently proves that this formalism, which is a subclass of devs, is actually closed under devs, closed under coupling, and actually does not increase the power of devs, but increases the ability and flexibility to characterize models in the biological application. Routed devs is another new subclass that hides the handling of routing information among devs component models, introduced by Blass in 2017, who also recently codified the diagrams that we talked about earlier between variants and subclasses. The routed devs defines atomic models that use routing information to authenticate senders, receivers, and transactions, and it makes it more convenient to employ or express the routing within network-like models, and hides the implementation of the interfaces that are provided. So the routed devs is a subclass of devs, and Blass has proved that it's closed under coupling, and is equivalent to devs. So it does not increase the range, but does increase greatly the ability to work with routed situations. Min-max devs as an example of non-closed closure under coupling, and it introduces the idea of ambiguous delay into the devs formalism, so you can say it's an extension or a variant of devs with an interval representation for the time advance function. Now, I won't go into detail, but the mechanisms by which the minimum and maximum time are kept track are defined for atomic devs, but are not easily extended to a coupled situation. So the min-max devs has not been proved to be closed under coupling. And there are some interesting questions that arise in trying to do prove that kind of coupling. Okay, now we'll take a look at iterative system specification and see how the concepts we've been discussing generalized to this more general framework. Iterative system specification aims to make systems concepts effectively computable, so a computational basis for modeling and simulation. They combine effective computation theories, such as in Turing machines, and also Weimar's system theory. And the difference between the two is that computation theory in computer science doesn't really have a concept of time in how it treats sequences of states or events, while system theory has a time base, puts everything on a global time base. And when you look at the devs subclass with the concept of events, actually then allows the events to occur in time, and therefore adds the time or temporal dimension to the effective computation theory, or what is studied in computer science. The result of combination is a way to specify systems in an event-like manner. That's exemplified by devs. Now, as an example, so far the Turing machine that we have studied specifies a well-defined system, but that has been within the context of devs. So what if we allow the tape elements not to be discrete symbols, but to have continuous durations and values that are continuous in their profiles? Also, what if a symbol comes in while a control is still processing a previous symbol? Because these are not discrete, then we can have overlap, and we really don't have any way of expressing that within the discrete event context as such. So we need iterative system specification to address such questions. The iterative specification then, as we have said, combines the system theory of Weimar's system theory with the effective computation concepts, and it allows the discrete events, which have abstracted away continuous and fuzzified boundaries, to be represented. But that raises the question of when is the result of this kind of these kind of definitions well defined. And so iterative system specification allows us to put more of what has been left out in devs back in, and then deal with it so that we have a good formal and mathematical handle on it. I'll now do a very quick exposition of iterative system specification concepts. More detail is going to be available in the third edition of Theory of Modeling and Simulation, expected to come out in mid-2018. First, we'll talk about input generators. These characterize discrete input and output events, but having finite durations. Such time-based event streams are characterized by generators. A generator has a length to it in time, Could be null, which has no values but has a time duration. Could be a constant that lasts a certain time, or it could be a pulse that has a certain duration. So the ability to put these generators together, one following the other, to concatenate them, allows us to represent events that stream over time, but which have durations and forms and profiles to them. But we also need a way to decompose such streams into unique generator segments, and a concept called maximal length segmentation extracts the longest successive generators to give us unique set of generators for a given time function, such that composing the generators in the order they were discovered reproduces the original segment. Now, how a dynamic system or input-output system handles a stream of input generators to produce a stream or segment of output generators is the essence of describing the behavior of a system, and it can be considered the formal representation of computing with generators. So we have a composition or concatenation of generators entering a system, and we have the transition function of the system that computes the state of the system at the end of a generator, given the state at the beginning of a generator. So you can see that if we can do that, then we iterate to compute successive states at the end of each generator, and then we have an output function that produces output based on those state transitions. What really happens here is that the system transition function summarizes the state trajectory that goes from the initial state to the final state. You can think of it as being originally computed in small step sizes, small state transitions. But for a generator, it's computed as a single jump from initial state to final state. And this is what provides the efficiency of discrete event computation, because all these small steps are being jumped through, having been pre-computed in effect in the system transition function. So now we have an idea of how to compute the system input-output function specified by generators. But now the question is, when is this resulting concept a real system? We can talk about atomic components that compute the input-output functions, and we can then talk about composition of component systems, where we have the input-output function of each component, and we have starting states for the components. But to compute their input-output, the input-output function, rather, of the composition of the coupled system, we really have to guess at what the input and output generators are that satisfy all the constraints imposed by the coupling relation and by the individual component input-output relations. This really does need for some theorem to tell us under what condition such an assembly results in a well-defined system. So we'll give some quick idea of what is involved. We can think about a closed system with timed transitions. This would be the resultant of a coupled model, where each of the states we're seeing here is actually a state vector, which is the element of the cross product of states of the components. So it's not as simple as it looks here. But with this kind of concept and recognizing that we have time advances, then the question is, under what condition do we get a well-defined graph that satisfies the right conditions? So there are two conditions, the determinism and progressivity. Determinism is basically that there's a single outbound transition from every state. So S2 and S4 are examples, because in S2 you stay in the state forever, while in S4 there's only one state transition out. Non-determinism is then when you don't have that situation, either because there's no trajectory emerging like in S8, or because there are more than one trajectories or outbound transitions like at S1. So we have a concept of determinism. But also, we need the concept of progressivity that requires the time advances always as we extend a trajectory. For example, the cycle of S4, S5, X6, S7 is not progressive because the time does not advance in that cycle, and so there's no way to once we get into that state, there's no way to say what time we are in and relate that to any other model that's progressing in time as well. So we see that the answer to the question of whether when an assemblage of component systems is itself a well-defined system is not an easy one. We can say the resultant of such a composition is well-defined if two kinds of conditions hold, the determinism and the progressivity. For determinism, we can say that for all generator segments, the input-output relations of the components are satisfied and the coupling relations are satisfied all together, all simultaneously. For the progressivity condition, we can say that the maximum length segmentation, which computes the time advances, satisfies the progressive requirement that time always advances as the segment or trajectory is extended. As an existence proof for the ability to actually satisfy these conditions that we just saw, I'll talk about a class of compositions we'll call active-passive. In this kind of composition, which is found in numerous information technology and process control systems, Each component system alternates between two phases, active and passive. When one system is active, the other is passive. Only one can be active at any time. And the active system does two actions. It sends input to the passive system that activates it, puts it in the active phase, and it transits to the passive phase itself to await subsequent reactivation. And in fact, the Turing machine components, when coupled together, provide an example of an active-passive composition. As you recall, the Turing machine decides on what the next symbol and move to send to the tape should be, and then it waits and goes passive while it's in the symbol to activate the tape. The tape then moves to the according to the move instruction and writes the symbol, and then produces a symbol that is in the position that sent to the control. And this alternation between activity and passivity is generalized in this concept of active-passive composition. And for such systems, the conditions that we just described are easily proved. Then it turns out that the iteratively specified systems can be simulated by Dev subclass of iteratively specified systems. So that involves encoding the generators coming into an iterative specified system. Now, in the third edition of Theory of Modeling and Simulation, we produced this kind of map of various subclasses of iteratively specified systems, showing how they can be defined and their properties, how they generalize existing formalisms, such as the high-flow formalism of Barros and the hybrid co-simulation of formalism of Nutaro, and also how devs can simulate any iterative system specification, as we just suggested. Now, here's an example of active-passive concepts that throw some light on the emergence of human conversational language interaction. From an evolutionary perspective, there was an emergence of a duplex channel allowing bidirectional communication between agents. So you have to go back and think about homonyms that were trying to hunt or cooperate in some way, and were unable to use language. And suddenly a language emerged, and how did that happen? They had to establish a discipline or protocol for when to speak, when to listen, among the other capabilities to do speaking and listening. But we want to focus on the discipline or the protocol. And the problem you can understand in talking with a friend on the phone, Skype, WebEx, where there's some delay or echo, and it's very difficult to maintain the proper phasing. When you're talking, your friend should be listening, and so on, conversely. And you see that when you have people debating on cable TV and attempting to talk over each other. From a systems perspective, actually, this is can be phrased as when does coupling from output to input of a pair of agents form a well-defined system. The inputs and outputs are currently occurring simultaneously in continuous time. Constraints must be simultaneously satisfied at every instance, and they must overcome the potential to get stuck in Zeno-like or singularities in which time does not advance. So the active-passive alternation is a solution, as we've seen, and that corresponds to this protocol for speaking and listening, where one agent is speaking, the other is listening, and one conversely, and this speaking listening activity passivity alternates as time proceeds. We can characterize this within devs, and this can then be studied as far as dynamic systems and how they can be modeled. Very quick mention of the iterative specification and its ability to extend the application of the devs bus concept. Devs bus concept is one that allows co-simulation of different models in the same overall framework, but each expressed in different formalisms, but put into devs compliance. For example, over HLA. And now we have the ability to express each of these different system formalisms within the iterative specification framework. And so we have multiple systems expressed as iteratively specified systems. And the devs bus is the mechanism by which the coupling that is specified to couple these kinds of systems is the devs bus provides that actual operating mechanism. So we have a extended version of devs in a distributed form, able to support multi-formalism modeling and co-simulation using the iterative specification. Now, to summarize some of the points we made about iterative system specification, you see it's a constructive formalism for general system specification. It's computationally implementable as an extension to devs-based modeling and simulation environments. It enables fundamental conditions for a well-defined system to be studied and formulated, and brings out the underlying fixed point and Zeno-ness issues, which is the progressivity idea. And we've seen that active-passive compositions provide existence solution to these conditions. And they are very common and very easy to understand. The emergence of natural language in the way we discussed is an example of a well-defined active-passive system. And we've seen a little bit about how the iterative specification allows us to consider a wide variety of possible iteratively specified systems, including the ones we know about currently, and couple them together, co-simulate them in a distributed simulation environment. We've also mentioned, but have not actually proved, closure under coupling for the iterative system specification, but we've given the conditions under which we get well-defined systems by doing such coupling. In terms of closure under coupling, For devs, it supports a number of important concepts. The abstract simulator justifies hierarchical construction and flattening for efficient simulation. We have talked about subclasses and variants of devs, and if we include iterative specifications, and this closure provides assurance that the class is well defined. It enables checking for correct functioning, especially when the coupling of models is cyclic or has feedback. And this allows us to define abstract simulators and real simulators that are based on them to actually implement simulations of these subclasses. Non-closure, when it turns out that a class or variance is not closed, is also challenging. It challenges us to construct the smallest closed superclass of the class that is being investigated. Might involve adding what might be needed in the formalism to obtain this such closure, and what benefits might ensue by adding these constructs. It might have implications for computational emergence in that closure and decoupling can imply ontological, may not imply epistemological emergence as a possibility. We leave that to another discussion and close with these ideas. Well, I've mentioned the Theory of Modeling and Simulation, third edition. Here's how the cover looks, and you can see it's emphasizing discrete event and iterative system computational foundations. And if you're interested in Dev's simulation, here's a listing of Dev's simulation environments available at SourceForge, including Dev Suite, PowerDev, CD++, Dev SymPy on Python, ADevs on C++, and BLE also on C++. There are also other environments, including MS4Me, which is the only commercial environment at this time.